Hello everybody and welcome to another video about GCSE chemistry. Today we're going to be looking at the rate of chemical reactions. Chemical reactions can occur at vastly different rates. Whilst the reactivity of chemicals is a significant factor on how chemical reactions can proceed, there are many variables that can be changed and manipulated in order to speed them up or slow reactions down. And in industry, chemists and chemical engineers determine the effect of different variables on reaction rate. And so what we're going to look at in this video is we're going to begin by looking at what rate of reaction actually is. Then we're going to explore the different ways of measuring the rates of reaction. We'll look deeper into chemical reactions by exploring collision theory, and then we'll finish off by exploring the 4 different factors that can affect the rate of chemical reactions. Now, before we look at the rate of chemical reactions, it's important to consider the different things that we might observe during chemical reactions. Now, there are 5 main things that you might observe, and I'll start with the one that's least important in GCSE chemistry, which is we might smell something that was not there before. The other 4 changes that I've got on this page are really common that you'll encounter them on GCSE chemistry, and the one on here, the bottom left, is that there might be a temperature change, and the piece of equipment that you might use to find out if there was a temperature change is a thermometer, so a thermometer. So a meter is for anything for measuring, and therm is to do with thermal energy. Then the one in the middle here, this is really common. This is probably the most common one for exam questions, and this is the production of a gas. Now, whilst what's happening is a gas is being produced, what you would observe is you would observe bubbling or fizzing, although my favourite word here, it's a little bit trickier to spell, is effervescence. And that just means bubbling, but it's a slightly fancier word. And so it's important to understand that if that crops up in any books that you'll come across. Now, the last 2 are less common to be the subject of exam questions, but you often get them in chemical reactions. And the one at the top here is you might see a colour change. And so I've got something going blue from being colourless at the beginning. It's important to use the word colourless for something like this, because if you use the word clear, that's not very specific, because a glass of apple juice could be clear, but it's very definitely not colourless like water. And the last one here, bottom right, is the formation of a solid. Well, more details about that on a different page. And in fact, not only could a solid appear, a solid might, in fact, disappear. If we have a look down here, we could have the exact same situation. We could start our chemical reaction with a solid, if we just turn this arrow the other way around, and chemical reactions might involve the exact reverse, where you start with a solid and it gets used up in a chemical reaction. Now, the rate of a chemical reaction, what is it? Well, put simply, it is how fast the reactants are changed into the products. Reactions can happen at all sorts of different rates. Sometimes they're really, really slow, like something like rusting. Other times you can have reactions that are really quick, like explosions. And other times you might have a reaction that is proceeding but not proceeding very quickly. So that might be if you put a bit of solid into a test tube full of acid and you get that effervescence from the metals reaction with the acid. Now, to find the rate of a chemical reaction, we need an observable change, like the ones that were on the last page. And we also need to time those changes. So what we absolutely need is we need a stopwatch, or you could also call it a timer. And so what you might do is you might time how long it took for something to go blue from the first page. And so if we had something on here and it went blue, and this one took 10 seconds to go blue, and then we had another experiment that was really, really similar, and this one went blue and this one took 20 seconds. And so because this was a shorter time, it is therefore a faster rate of reaction. To explore that idea in a little bit more depth now we've said that we've carried out some experiment where we've timed something. If we are timing how quickly one of two things happens, so either how quickly the reactant is used up or how quickly the product is formed, we then need to know what we're going to do with our two results, the time and the amount of product that we've made. So there's two relationships that you could use. They are very, very similar indeed. And first up then, the mean rate of reaction could be found by taking the quantity of reactant used and dividing it by the amount of time it took to make it. Alternatively, but really, really similarly, we could take our calculation for the mean rate of reaction by doing not the quantity of reactant used, but the quantity of product formed. And again, we would divide that quantity of product formed divided by time on there. Now, in practice, what is far easier is to do the bottom one, to look at the product that is formed, and therefore we'd be using that relationship on here. That is far more frequently comes up in a test, and it's actually in practice much easier to do, as you'll see on the next few pages. Now, to finish with what quantities, because I've used the word quantity, what quantities are we actually talking about? Well, the quantities might be a mass, which would be measured in grams, or they could be a volume, which will usually be measured in cubic centimetres, cm cubed. And last of all, less frequently and definitely only on the higher paper for chemistry, is it might be in moles, which has got the symbol mol. And time is normally in seconds. And alternatively, it could be in minutes, but not very often. The units that you have to use for rate of reaction depends on what it is that you're actually measuring in the chemical reaction itself. In general, the units will be something per second or something per minute. And that something depends, as I say, on what it is you're actually doing. So let's look at a first situation here where we're measuring a change in mass. So what I've got in this experiment is I've got a conical flask full of acid. It's called a conical flask because it is a cone shape. Conical flask. And what I'm going to do is I'm going to put into that acid, I'm going to put a piece of calcium carbonate, and I've got some cotton wool as well. So what we do in this reaction is we get all of our chemicals and our cotton wool and we put it on a balance, and we'd find out what the mass starts at. So I've made up a number on here. And then, as the reaction was ready, we would take our calcium carbonate, so I'll rub it out, we've taken it off from there, and we would then put it in with the acid, and that would then start to bubble. And before it starts bubbling too much, what we would do is we would take the cotton wool plug, and we would put that into the top of the conical flask on here. Now what that does is it doesn't actually stop the gas escaping, so because it's cotton wool, the gas can escape, but there is not any acid spitting out, because if the acid could kind of jump, because if something's really bubbly, the liquid might spit, and if the acid could jump out, then the mass would drop. And what we want to do in this experiment is we want to look at the mass of the gas that is escaping. So if we've got calcium carbonate that's a solid, and we're reacting it with hydrochloric acid, which is a solution, we're making carbon dioxide gas, and we're making calcium chloride, and we're making water. And of course, what's happening is the carbon dioxide is leaving and so the mass is going to go down. And so over time, let's say that that mass drops down to 184.75 grams. So that is a decrease, if we have a look at the difference between the two, of 2.00 grams. Obviously the numbers are not likely to be that nice in an actual test. So what do we do with that? How do we calculate the rate? Well, the rate is found by the change in a quantity, like we've just been talking about, which on this occasion is the mass. So 2 grams is the change. Now let's say this experiment took 2 minutes for this 2 gram decrease. So the rate of reaction could be 2 grams divided by 2 minutes, which would give us a rate of reaction of 2 divided by 2 is of course 1. 1 gram per minute would be the rate of decrease in mass. Alternatively, we might have been asked to put this into grams per second, in which case we need to do 2 grams divided by 120 seconds, because there's 120 seconds in a minute, and then in that case we would get an answer of 0.0167 grams per second. And this experiment is quite good because balances are very, very sensitive. And so what that means is you can get lots of decimal points and you can ultimately end up with an answer that is very, very accurate. So the equipment is sensitive. That means it's got a lot of decimal points. And then because of that, you can get very close to the true value, which is what it means when we're talking about to be accurate. Now, a downside of this experiment is actually that we are releasing gas into the atmosphere, and that's built into the experiment. Now, that's okay if the gas is not dangerous, but if it is, obviously, that is a problem that this gas is escaping. The other problem in this experiment is for gases that have got a very, very light mass, such as hydrogen. Hydrogen's got a relative molecular mass of 2, and so that means that the mass will not change very much at all for hydrogen in this experiment. If there's a gas being produced in a reaction, you could also measure the rate of reaction by collecting that gas that had been produced. Now, I've got 2 pictures here because there are 2 different methods of collecting gas in a reaction. So both of these conical flasks have got hydrochloric acid in, and we've got a timer on the left-hand side. And so one method is to put a bung into the conical flask and to connect that bung to a gas syringe. Now, gas syringes, I'm not the best artist, but the crucial ingredient for a gas syringe is that you've got a scale on here, and that scale allows you to measure the volume of gas that you're collecting. Now, at the end, let's have a plunger at the end, and our gas syringe is here. And so what would happen is the gas syringe would have a plunger that would move outwards over time, and in here, this is where the gas will collect, and you can measure the volume that you have collected as time goes on. Now, obviously, you'd have to have put something in there. That's the calcium carbonate again. Now, you can do the exact same thing and get data that's almost as good by using some slightly less high-tech equipment, which is where you get your delivery tube again. That's what this glass tube is. It's the same for both experiments. You have a delivery tube, and that delivery tube is put into a bowl or a container of water, and that water has got a measuring cylinder in it. And the measuring cylinder, again, has got a scale on the side that allows you to measure the volume of gas that has been produced. The measuring cylinder is also full of water. The measuring cylinder is also full of water. And so what that means is, as time goes on, as the reaction proceeds, these bubbles of gas will rise up to the top, and the gas will collect here, and the water level will go downwards as the gas displaces the water. And so when you want to measure the volume of gas that you've collected, it's nice and easy. If you've got the gas syringe, you just read this value here from your scale. With the water displacement experiment, it's a little bit more awkward because you're measuring this line on here, and what you're measuring is the volume of gas, not how much water you've had. You're measuring the amount of water that's left. So you start here, which should hopefully be 0, and it goes down over time on your water level, but the volume of gas that you collect goes up. Now, this experiment is really commonly the subject of an exam question, so that's something to keep in mind. The gas syringe method is really good because gas syringes usually measure to the nearest 1 cm cubed, so that means they're quite sensitive. The biggest drawback of this method is probably, well, it's common for both of them, but it's probably particularly common with the right-hand side one, because what you end up having to do is you get your marble chips or your calcium carbonate, you put them into the acid, it starts fizzing, and then you have to get your bung in. So it's the time between adding your chemicals and then getting that bung in. Because what will happen then, and by the bung, that's this bit, what will happen then is there'll be some time lag and then some gas could escape. And the gas escaping means that you won't be collecting it, and so therefore your volume is smaller than you think it should be. In terms of how you'd process results over here, the rate of reaction would be the quantity. So let's say we've made 60 cm cubed of gas and it took us 3 minutes to do it. Well, then our rate of reaction would be 60 divided by 3, which is 20 cubic centimetres per minute. Or if we wanted it to be in centimetres cubed per second, we'd have to do 60 cm cubed divided by 180 seconds, because that's how many seconds there are in a minute, and that gets us 0.5 centimetres cubed every second. The final method that you can use to work out the rate of reaction is if you are making a precipitate. Now, a precipitate is a solid that forms during a reaction that involves solutions. So this is very common for the required practical style questions. And so what you have in this experiment is you have some chemical, which is normally an acid. You would make a mark underneath the conical flask, and you would be looking down through the conical flask. That's meant to be an eye. You'd be looking down through the conical flask, and over time, what would happen is something would form that means that you can't see that cross very well. And then once enough of that chemical has formed so that you can't see that cross at all, the cross disappears. Now, obviously, it doesn't actually disappear. It's just blocked and you can't see it anymore. So then you stop the stopwatch. The situation where you're likely to come across this experiment is called the disappearing cross experiment, and it involves a chemical called sodium thiosulfate. And you get a cloudy white colour. And what you're doing in this experiment is you're measuring the cloudiness or the turbidity, which is a fancy way of saying cloudiness. In terms of good and bad things about this experiment, the good thing is that it is incredibly simple. The bad thing is that not everything involves colour change, so it's not always suitable. Because if you're not making a solid, or you're not making something that's got some colour that could obscure that cross, then this experiment just won't work. Sometimes an exam question might ask you to suggest a method for measuring the rate of reaction. Now, this sounds like a complicated question, particularly when they follow it up with an equation that looks very complicated. But actually, all you need to do is you need to look at these little letters in brackets after every formula in the equation. And what we're looking for is we're looking for a state symbol that gives us big clues about how we follow this reaction. And the one that we are interested in is not any of these other ones. We're only interested in this little G here, because that little G tells us that we're making a gas in this chemical reaction. And so actually we could use either method 1 and measure the mass drop, or we could use method 2 and collect that carbon dioxide gas and measure how much we've got over time. This second equation, we've got a solution, a solution, a solid and a solution. Well, we're going to be doing method 3 here because we're making a solid precipitate of copper hydroxide. And we would simply measure the amount of time it took for the copper hydroxide precipitate to cover up a mark. Let's have a look now at collision theory. Collision theory explains how various factors affect the rate of a chemical reaction. And according to collision theory, chemical reactions can only occur when reacting particles will collide together. They also need to have enough kinetic energy for the reaction to be successful. So these two particles, as they are here, this one needs to knock into that one, and we need to have a forceful collision. So in slightly more formal terms, the rate of a chemical reaction depends on the frequency of collisions, in other words, how often they collide, and the energy transferred during these collisions, so in simple terms, how hard they collide, how forcefully they collide. Now, it's really important to keep in mind over the next few minutes that anything that affects these two things is going to change the rate of a chemical reaction. So the frequency of collisions and the energy transferred during those collisions, in other words, how hard these particles collide together. We're now going to take a look at the factors that affect the rate of a chemical reaction, and there are four that we're going to look at. The first of these is surface area, which is to do with reactions that involve pieces of solid. And surface area depends on the size of these solid pieces. And so we have a general rule that you need to remember, is that the larger the surface area will give a faster rate of reaction. I'm just going to write ROR for speed there from now on. The faster the rate of reaction. So we can illustrate that with a diagram. So in this box on the left hand side, I'm going to draw a piece of solid. Here is that piece of solid on there. On the right hand side, I'm going to draw hopefully the same volume of solid, but it's going to be in smaller pieces. That will do on there. Hopefully that's the same volume. And so what we can see if we have a look at just tracing the surface of this particle, so that's the surface area of the piece of solid on the left. On the right, if we trace the same pathway, you can see I'm using a lot more yellow ink on here to cover up all the surface of the particles on the right hand side. So smaller pieces of solid, if it's got the same volume, has a larger surface area. And so what that means is if we have something that's going to react with the solid, let's draw a few particles of acid, say, then there is a greater surface area for the particles on the right hand side, and so collisions are going to be more frequent, and so that's absolutely vital. For the larger surface area, collisions are more frequent. And therefore there will be a faster rate of reaction because more frequent collisions, like we said on that previous slide about collision theory. Just want to spend a little bit more time talking about surface area by looking at something that we call surface area to volume ratio. Now, this is a complicated concept. You'll measure all these quantities in maths and you'll use them in biology when you're looking at animal adaptations and heat loss. If we consider the cube on the left-hand side here, it's got dimensions of 2 centimetres by 2 centimetres by 2 centimetres. So measuring the volume of this cube is nice and easy, 2 by 2 by 2, which is 8 cubic centimetres. If we look at the surface area for this cube, the surface area, so the area of this face that's coming out towards us, is 2 by 2, which is 4 centimetres squared. But there are 6 faces in total. There's this one, and this one, and then there's the 3 faces that we can't see. So we need to multiply that number by 6, and we get 24 centimetres squared. So the surface area to volume ratio is 24 centimetres squared divided by 8 centimetres cubed. So that gives us a surface area to volume ratio of 3. Now if we consider a smaller cube, the volume of this smaller cube, if we make this cube 1 by 1 by 1, the volume is going to be 1 by 1 by 1, which is 1 cubic centimetre. The surface area of this cube, again, considering this front face, surface area is going to be 1 multiplied by 1, which is 1 centimetre squared. And then we need to multiply that number by 6 because of the 6 faces, so we get 6 square centimetres. And so the surface area to volume ratio for this cube is going to be 6, because 6 divided by 1, which is going to be 6. And so a smaller cube has got a greater surface area to volume ratio. Now, that's relevant even though if we consider the fact that this smaller cube is smaller, if we look at how many cubes would fit inside, so if we got this big cube and we split it up into pieces, we would end up with 8 of these little cubes. And so the total volume, in fact, wouldn't be 1, it would be 8 cubic centimetres. The total surface area wouldn't be 6 centimetres squared, it would be 8 multiplied by 6 centimetres squared, which is 48 square centimetres. And then the surface area to volume ratio would be 48 divided by 8, which is 6. And so again, we've got the same surface area to volume ratio, we've just got more cubes of the same size. So having one big piece compared to a smaller piece, it's not just about the surface area, it's also about the surface area to volume ratio, which is twice as big in this example for the smaller pieces. Let's move on to have a look at the second factor, which is concentration, or if we're talking about gases, we're talking about pressure. So just a quick reminder, concentration is a measure of the number of particles in a particular volume. And so if we consider a lower concentration on the left-hand side with just maybe 4 particles in there, then we've got a higher concentration on the right-hand side. I'm going to draw more of them. And so because we've got a higher concentration, we've got more particles per unit volume. More particles per unit volume. The chances of a successful collision are going to be greater, and so the language we should use is more frequent successful collisions. And because of that, it will therefore be a faster rate of reaction. And it's the exact same idea with gases, only we're talking about pressure. And so if we increase the pressure for gases, what we're doing is we're putting the particles are more squashed together. And so the particles are closer and they're in a higher concentration, and there's more particles per unit volume, and once again, more frequent successful collisions and therefore a faster rate of reaction. Temperature change is probably the most obvious thing that will affect the rate of a reaction. And so I've just dived in at the beginning by telling you the answer, which we already know, which is that a higher temperature will be a faster rate of reaction. And the reason for that's twofold. So first up, if we consider the lower temperature, the particles at the lower temperature have got less kinetic energy than the particles at the higher temperature. And because they've got more kinetic energy at the higher temperature, let's draw the same particles, they're going to be moving faster. And because they're going to be moving faster, they're going to collide more frequently. And because they're colliding more frequently, it will be a faster rate of reaction. And now, not only do particles collide more frequently, they also collide with more energy because they're moving faster. And that, again, that's the second reason in collision theory for particles having a faster rate of reaction. So we've got them moving faster, so they're colliding more frequently and they're colliding with more energy. I'd like to explore this idea of energy in a little bit of greater depth now by looking at a concept called activation energy. Activation energy is the minimum amount of energy particles must have to start a reaction. So if we consider a situation where the temperature is cold and we've got 10 different particles here with different amounts of energy, let's not worry about units because energy can have lots of different units. So let's just put a number onto it. So if the minimum amount of energy needed to start a reaction, let's say this activation energy was something like 12, the energy of activation is 12, then what that means is if we have a look at the particles, not very many of them, this one and this one and this one, have got enough energy to react at this cold temperature. If we were to make it warmer, what we would be doing is we'd be giving these particles more energy. So instead of the energy that they had before, I'm just going to double all of these numbers. Now, if we have a look at the activation energy still being 12, what we can see is that more of these particles now have that required minimum to start the reaction going. This one does, and that one, and this one, and this one, and this one. And in fact, now from my 10 particles, only 2 of them don't have enough energy to react. So we can see that this reaction is going to be faster because more particles have got this minimum amount of energy. This idea of activation energy leads us on to our final factor that affects the rate of reaction, which is catalysts. Now, catalysts are defined as something that speed up a reaction, but it's not changed and it's not used up either during that chemical reaction. And how they do this is they provide a different pathway for the reaction that has got a lower activation energy, which is the equivalent of if you imagine you've got a hill and you're here trying to get over the hill. You can go over the top, or you can follow a different pathway, which is to go through a tunnel through that hill. If we have a look at my example again for these particles, if we look at, again, let's stick with an activation energy of 12, only this particle and this particle and this particle have got enough energy to react. But when we use a catalyst, the catalyst will reduce this activation energy. So let's reduce this activation energy by half. Now, so the activation energy is now 6. And so what that means is this particle's now got enough energy to react because the minimum has been decreased. And this one has, and this one has, and this one has, and this one has, because the catalyst has meant that the activation energy has dropped from 12 to 6. And so now, as a result, all these additional particles have got enough energy to react, whereas before they did not have enough. An important thing to note about catalysts is that different catalysts will be used for different chemical reactions. You can't just use the same catalyst with all the different reactions that there are in the world. An example of this that's really effective is actually biological catalysts, which are called enzymes. These biological catalysts, enzymes, work in all sorts of biological systems, but let's just focus on our body. In our digestive system, you have a number of different enzymes that help to break apart our food from larger molecules such as proteins into smaller molecules such as amino acids. But the enzymes called protease enzymes can't break apart all the different nutrients that we've got. They can only work on proteins. We need different enzymes to break up the different nutrients in our diet. And just like that, we need different catalysts for different chemical reactions. An experiment where you might have investigated catalysts is looking at a chemical called hydrogen peroxide, which has got the chemical formula H2O2. Now, in this experiment, what you do is you get some hydrogen peroxide and you let it decompose, you let it fall apart. So the hydrogen peroxide falls apart. And what it does when it falls apart is it makes oxygen and it makes water. And crucially, this oxygen is a gas. And because it's a gas, we can collect it. And we can measure how much gas we've collected over time and work out the rate of reaction. Now, to see the effect of a catalyst, what you would need to do is you would get a catalyst, you'd need to put it into the hydrogen peroxide and see if that decomposition speeds up. And it will do if you use metal salts, for instance, manganese dioxide. And so what that will do is that will make this decomposition a lot faster. We'll get our oxygen gas formed a lot more quickly, and the oxygen will move on through this delivery tube and it will collect in the gas syringe that we've already looked at. And you could see which catalyst was the best catalyst by looking at which metal salts produced oxygen the most quickly with hydrogen peroxide. But you'd have to keep things the same. You'd have to use the same mass each time of the metal salt to see which one was the best. To explore catalysts in greater depth, we need to look at something called energy profiles. Now, an energy profile looks like a graph. And we've got energy on the y-axis and we've got time on the x-axis, although sometimes it might be written as progress of the reaction. Because what our energy profile does is it shows us how much energy the reactants have got at the beginning, and it shows us how much energy our products have got at the end. And so I've chosen to draw this situation here where the reactants have got more energy than the products. So as time goes by and the reactants turn into products, energy will be given out to the surroundings as heat. And this is called an exothermic reaction, because heat energy, thermal, is exiting exo. So heat energy is exiting or being given out to the surroundings. And what that means is the temperature of the surroundings will therefore increase. Now, what this energy profile shows us, it doesn't just show us the starting energy of the reactants and the finishing energy of the products. It shows us how the energy changes over time. Because as we learned earlier, the energy needs to go in to start a chemical reaction off. So what that means is the chemicals have got more energy than they had at the beginning. And this is called the activation energy, the energy that the reactants need to gain to start the chemical reaction going. And then the reactants will lose their energy as they turn into the products. There is another type of chemical reaction that's not exothermic, it's endothermic, and it looks really, really similar. The only difference, so we've got energy and we've got time on here, but the only difference is that this time the reactants have got less energy than the products, but the curve is the exact same shape. Energy has to go in and energy comes out, and this energy is, again, the energy that goes in is the activation energy on there. This type of reaction is called an endothermic reaction, and that's because, again, it's about thermal energy, so thermic, and this time the heat energy is not going out, it is going in. So the heat energy is going in to the chemicals, and what that means is that the surroundings get colder, and so for an endothermic reaction the temperature is going to drop because energy has come in from the surroundings. The significance of these energy profile diagrams in terms of catalysts is that catalysts make the activation energy smaller in each case, and so if the activation energy is not so high, then the energy profile doesn't go up as high either. And so this is the activation energy with a catalyst. The activation energy is smaller with a catalyst. But the hill still looks the same sort of shape, it's just not got such a tall top. And we have the same situation in the endothermic reaction as well. The activation energy isn't so high, and so we can see that the hill is smaller, but it starts and finishes at the same place in both of these cases. Okay, that's the final part of today's topic, so thank you very much for listening. I hope it's been interesting, and we'll see you again soon. Bye-bye.